bit about the homework. I know it's 29 graded, which you should also have turned in. The 28 you should have just got back if you turned it in, yeah? A couple things. First of all, sorry, actually I take it back. I have a couple in here that I haven't graded that you might have turned in. Mike, I do have yours. Sorry, I don't have it graded yet. It's added to your own stat. You do have that. You have yours. Sorry. Okay, so, all right, so I guess this is, I gotta warn you real quick about this class. Let's just think about that. You really need to make the most of every homework. I understand you're busy, and I understand it takes a long time to do this homework. I understand that, I know. But I gotta warn you, it's not like Algebra 1 where you're gonna get 4 weeks to get something mastered. You're gonna get practice for maybe 3 days, and then it's gone, and on to the new thing. And if you go off 2 days, you're not gonna understand this time. And you've got to make the most of every problem, because it goes, the amount of practice per concept is not like you're used to, okay? It's gonna go fast. So you really have to, when you turn in a homework, you have to say, yes, I really definitely understand that now, or I definitely don't, and if you don't, do something about it. That goes to whether you actually are looking and seeing the sites or not. So a couple things, just to as an example, 28, the things you should have seen. Okay, number 28, set 28, number 3, for example. I had a lot of people not use the end behavior. There's a lot of concepts to this, but the end behavior is one of them. What's the end behavior to this? 2. Okay, that's a good start. The limit is 2. Now, you know what that means and use it. The limit is 2. Great. What does that mean? That means as x goes to infinity, y goes to 2. And so your graph out here, inside it does all this crazy stuff, and I'm not going to get into that again. But out here, your graph should not do that. Is that as x goes to infinity, y goes to 2? That's not as x goes to infinity, y goes to 2. That's as x goes to infinity, y goes to 2. So understand what you're looking at here. I had people do the limit, but they used it not at all. Okay, so understand how that's used. Second, I am not sure if you understand still when you do a tangent line, it's actually a 3-part process. There's a point, a slope, which you find by taking the derivative, and then point slope form. I have some people just giving me a slope. That is not the question. That is not finished. Also, make sure you can use your calculator to find a derivative at a point. Okay, that was supposed to be calculator. If you're not sure how to use your calculator to find derivative of a point, please ask. We need to go over that. Okay. If you do, we can go over others. All right. These, I had some people, this is just some people here and there, by the way. There's some people that are just doing beautiful. I have people just circling an answer here. Now, even to the best calculus student, I would, a BC student could do these in their sleep, but they would still show work. Okay, it's not just circle and answer. You should be saying, I understand that these are derivative limits, and you should be communicating. This is the derivative of what? That's kind of hard to interpret. The idea is this is more of a, instead of f of x plus h minus f of x over h, it feels like they're doing the definition of the derivative specifically at an x of 8. So you should say, I understand it's a derivative. Boom, part 1. Second thing is derivative of what? What's the function? In this case, it's the cube root of x. And then you need to say, I understand that it's the derivative at an x of 8. Okay, then you say, all right, now I roll with my derivative rules. The derivative of x to the 1/3 is 1/3 x to the negative 2/3 at 8. That's the process, okay? I mean, if you're really bright enough to do all that mentally, good for you, but I still want to see it. Okay? All right, same goes here. You should say, hey, this is the derivative of what function? Write this above it. It feels like it's not added x, because there's no x's here. It feels like it's added x of a half. But what's the function? 8 x plus h to the 8, or 8 times the function to the 8th. At what value? At what number? What x are they putting in? At 1/2. Okay, that's the thought process. You need to be able to recognize that limit is a definition of the derivative problem. Then, after you interpret it, you actually do the derivative, and then give the answer. Okay, that's what I expect to see. This same deal. A lot of people lost points on this. The rebuke I have here is that use your notes. Okay, it bothers me is a big old question. I did one just like that in the notes. 6 steps right next to it. Exactly what to do. Use your notes. Use your notes. All right, tells you exactly what to do. A lot of people blew this off. This is a big idea of calculus. Estimating an instantaneous rate of change at a point with an average rate of change. This is a decent estimator of the change at that. That's what this is all about. But it is an estimator. So when I say what's wrong with this, the derivative at a point equals the slope between 2 points, it doesn't equal. It's an approximation. Not equal, okay? So a lot of people didn't even do that problem. It's an important one. I want to make sure you do that. And this is on me. This is kind of a big idea that I put on with the intention of talking about it. But let's go over it here. S prime at 2. Most people did the derivative correctly. 6t plus 4 at 2 is 16. The interpretation is what I'd like to talk to you about. This notation, Newton's notation, it doesn't lend itself to interpretation as well as Leibniz notation does. So if I were to rewrite this, this is the derivative, which is to say ds dt. Now that's, d stands for infinitesimally small delta. So this is change in s. Well, what is s according to this? S stands for the position. Change in position over change in time. What do you call change in position over time? It's a rate. It's the velocity. If you were to attach units to this, the top 16, the units for position are meters. The denominator, which I put in there is 1, the units for time are 1. ds dt, change in position over time, is velocity. The big idea then is the derivative of position is velocity, because the derivative is a rate of change. The rate at which position changes is the same as velocity. So what's the derivative of velocity? What's the change in velocity over time? What do we call that? Acceleration. The derivative of velocity is acceleration. Okay. All right, and then this, I don't have a lot to say to this. Just be sure you can do this well because it'll be on the test. Yes. You got what? Why? All right. Okay. That's it. So, the fun sheet today. Yay, fun sheet. Yeah. Worksheet has such a negative connotation. Worksheet, but it's a fun sheet. Hey, fun sheet. Am I right? I'm excited. Okay, so fun sheet for you. It's really shouldn't be that much work, but it is good review for the exam. I will also probably have an optional review for you tomorrow, but that is an assignment. It's due tomorrow. And it's just a review of topics. Sometimes in this class, I said it goes too fast. Sometimes maybe it take a few days to go over a few things, and hopefully that'll do that for you. All right, so now it's just questions on set 30. Okay, questions on set 30. Hit me. 1, 3, and 25. Is that what you said, lady? Yes. 20. 24. Got 25. 22 part 2. 17. Did I hear that right? Okay. 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 If I'm not on your problem, I don't mind if you work on tonight's homework. Just keep an ear out for your problems so I don't waste my time back here. Set 30 number 1, yeah, that's back in the day.
How would I remember that? Oh my god.
Algebra 3, yeah. Did he do it by a table? How did you teach it?
I don't think I actually mentioned it.
Should have? Okay, that's good. Did that stick with you, Kaylee? Okay. All right. So, I could go at this a couple different ways, but let me go at it this way. So it says Dean Hudson drove M miles per hour for H hours. Got there 2 hours late. How fast?
No, ask somebody else.
Okay, so that's the equation. And then that's just, here we go. You could do this by a table, and I'm going to do that if this doesn't stick. But I start with the question: how fast to get there on time? What do they want me to find? A distance, a rate, or a time? A rate, right? A rate. If I want a rate, then I would need to know the distance for the trip and the time. Okay? If I can find those two things, then I will be good to go. Well, let's find the distance. They don't specifically give it to me. So that's unfortunate, but maybe we can get it. It says she drove M miles per hour for H hours. Can I find the distance from them? Yeah, the distance is rate times time. In the trip they did, what was the rate? 10. What was the time? H. So what was the distance? MH. Okay, so the distance of the trip is MH. Cool. Now, I also need to get the rate, I need to find the time. Well, it says the first time they did it in H hours, but they got there 2 hours late. So if I want to get there on time, if H hours is 2 hours too late, then what should the time be? H plus 2 or H minus 2? Do I want it to take less time or more time? Minus 2. I need to do 2 less than the previous time to get there on time, right? So the time I need to hit is H minus 2. Well, there you go. There's your answer. Okay, so miles per hour, the units, but that's what went through my head. I can do it a different way if that doesn't stick. Does that make sense? Okay, 3. Question on 3 still. Whoever asked that, do you still have a question? Yes? Okay, I'm happy to do it. I just want to make sure that you're paying attention. All right, number 3. 3 is tangent from negative 2 pi to 2 pi. I am happy if you do more, that's fine. So let's go with this. Do you remember the shape, and do you remember the asymptotes? And if the question is, how do I remember that, then we can talk about that. Can you remember the shape of the asymptotes? Yes. Yeah. The shape is like a cube, sort of. And the question is, what are the asymptotes? Now, if you can't remember that, think your way through it. The asymptotes happen because you have a zero in the denominator. So the asymptotes are where cosine is 0, and that's at pi over 2s, 3 pi over 2s, and so on, plus or minus. Okay? So me, I would probably choose a scale that locates pi over 2s, whether it be every couple boxes or every 4 boxes, that's up to you. I didn't really give myself enough room, but that'll get going. I have asymptotes at negative pi over 2, and 3 pi over 2, and 5 pi over 2, and so on. Okay, good deal. Now then, after that, there are 3 points that I expect you to locate. Those aren't the actual points. Tangent of 0 right in the middle. Tangent of 0 is 0, right? Pi over 4 is between pi over 2 and 0. So what is tangent of pi over 4? 1. Sine over cosine is 1. Now, that's what I expect you to show a vertical scale. So whatever you choose to show for 1, I should see a point at pi over 4, 1, communicating to me that you know how to stretch a graph when necessary, or what the vertical growth factor is. So I should see 3 points per curve, and the asymptote's clearly done. After you get one curve, you just kind of wallpaper the rest. Show the rest of the pattern continues. That's bad. That inflection point. Okay, always make sure that you go to over the entire space provided, because you're showing where the points are that solve the equation and whether or not. Okay? Does that make sense? Okay. So, know the shape, know the asymptotes, and roll. Number 25, is that still a question? Somebody need 25 still? Okay. You had an epiphany? Oh, Mr. Griffiths, now I'm nervous. So 25, you just you figured it out? Okay, 20. Yes? Don't be shy. Say yeah. Advocate for yourself. Okay? College, man, survival of the fittest. You got to be aggressive with that question. Yes, 20. Hit me. Okay. All right. 20. 20 is straight up out of the book. Okay. So if 20, you might have been just not quite sure what they're asking. Really, they were just saying points on the unit circle. So when they say point 1 here is at 5 pi over 6, remember the whole unit circle is the idea that if you have a circle with a radius of 1, then the adjacent side and the opposite side and all the trig boils down to really simple. If, for example, if I say the cosine of this angle, because it's adjacent to a hypotenuse and it's the unit circle has a radius of 1, and the unit circle, the hypotenuse is a non-issue, and it's just that the x is always the cosine and the y, or the adjacent side is always, or the opposite side is always the sine. So when they say what's the point on the unit circle, they are asking for the x and the y, and the x is the adjacent side, so cosine, and the y is the opposite side, so sine. So point 1 is merely saying what's the sine or the cosine of 5 pi over 6. What's the cosine of 5 pi over 6? Root 3 over 2 or negative root 3 over 2? Negative root 3 over 2, and the sine of 5 pi over 6 is 1/2 positive. Okay, the other point was at negative 5 pi over 6. If you go down, that's a negative angle. Negative 5 pi over 6 puts you at point 2. It's still x and y. X is still the adjacent side, so cosine. Y is still the opposite side, so sine. What's the cosine of negative 5 pi over 6? You get the point, so I need to continue? I feel like that. All right, I guess let me know if you still don't get it. 24 is still a question. Okay, 24. Yeah. So this takes you way back to Algebra 2. And I surely do not expect you to have this idea memorized. It's certainly not a big idea in calculus. It's just trying to keep it from being forgotten wholesale. This is the kind of thing that would show up on a SAT test. There is both a conceptual way of doing the problem and a memorized shortcut kind of way to do the problem. You know that this is x given. BC is x minus 1, and BC is x minus 2. Does anybody remember the shortcut kind of rule? All right, so the rule is that there is a relationship between the outside and the whole of one segment and the outside times the whole of another, and the product is equal. Now, where that comes from is a similar triangle problem. You get that idea by actually drawing overlapping triangles. You get proportionality of sides, and so that's not so whatever fact. If you really had to come up with it, I would go about it in a similar triangle way. That's how you get that idea. That said, then, outside times the whole. Here, the outside is x. The whole is the same, and so I would also call that x. On the other one, the outside is the segment outside the circle, is what I mean by that, x minus 1. The whole, then, is the whole segment. What's the length of that whole segment? 2x minus 3. With that, then, you're in quadratic solution territory. So if you FOIL that out, first, outer, inner, last, get everything on one side. Does this factor? I get a big no on that. Okay. So what are your other solution methods for solving quadratic besides factoring? Quadratic solution, complete square if you really want to overachieve and impress someone. Yeah. Okay. Are you good from there? I assume you can do the quadratic form. All right. How about 22 part 2? Is that still a question? Okay, 22 part 2. We're looking at use a graphing calculator. Okay, so, this is replacement? Oh, I see what you're saying. Good question. I'm so glad you asked. Okay, this one I'm going to actually paste in so I don't draw it poorly. Now this is called curve sketching, and it is a fairly large idea of calculus and something that we're going to gradually get better and better at. But I definitely on this go around didn't expect it to go flawlessly. All right. So you're okay with the reciprocal idea? Whose question is this? Okay, you're okay with the reciprocal idea, which we talked about yesterday. We're talking about just the derivative part, right? Okay, so good. Do the other one? Yeah, okay. Let's do the derivative first, and I'll come back and do the reciprocal one as well. They're both pretty high concept. All right, now, this is the idea. And again, we're going to come back to this over and over again. So just gradually stick with me here. Remember, when you draw the derivative, you're drawing or recording the slopes. A little bit like we did when we tried to find the derivative of log and sine and cosine. We drew slopes to try and get a picture of the derivative. Let's start here. There are two really important places on this curve. They are called extrema. Extreme points, relative mins and maxes. Now, this relative max, if I draw the tangent slope there, what's the tangent slope? 0. Okay. Now that means that at this x, whatever it is, ballpark estimate, just a little less than -1, the slope is 0. I would then show that here by saying a little less than I scaled this to spread it out a little more. So I'm going 2 boxes to 1. A little past -1, the slope is 0. Well, at an x of -1, the slope is 0. Remember, when you're saying f prime, you're saying what's the slope at that x? Okay, or the rate of change. What's another place then, ballpark, where the slope or the derivative is 0? Ballpark? 2-ish, somewhere in that. So, if I also record the slope is about 0, is 0 about at 2, then I'm starting to get something. Now, those are the only places that the slope is 0. So everywhere else, if the slope is not 0, then it must be positive or negative. So let's get into positive or negative. How about less than -1? If I draw tangent slopes there, what kind of slopes are those, positive or negative? Positive, okay? Now if they're positive slopes, then they're positive derivatives. And if I graph positive outcomes, those should be above the x-axis. So I'm going to graph here. These are really steep slopes here, yeah? And as we get closer and closer, the slopes get flatter and flatter and flatter. And so I would expect big positive slopes here. But as I get closer and closer to -1, I get smaller positive slopes. So that would mean then that I am getting big positives here, way out here. But as I get closer and closer to -1, they get smaller, smaller, and smaller. You follow? Yes? Okay. What about the slopes between the other two zeros, between -1-ish and 2-ish? What kind of slopes? Negative. So where will my derivative graph be? Below the axis. Until it has to be 0 again, so I guess it has to come up and meet that guy. And then after 2, the slopes go back to positive. That then is the derivative. And there's something else really cool in there. Ballpark, what does that look like function-wise? What power polynomial does that look like? X squared? Oh, you're thinking this one's x cubed, right? Now surely there's more going on to it, but x cubed-ish. Cool. What's the derivative of an x cubed function? 3x. Does that look like exactly what it should be? The parabola derivative, right? Yeah. All right. So use that. I mean, there really should be two thoughts going through your mind. X cubed graph. I'm expecting an x squared derivative, but also that actually have place of the curve. All right. What about the reciprocal? Are we? Let's start there. I'm going to clear this guy off now because this is totally different thinking. All right, the reciprocal idea starts with zeros. Where f is 0, or where this guy has x-intercepts, this is 1/0, so vertical asymptotes. So I'll have vertical asymptotes at -2. And where else? 0 and 3. Okay, that's one big idea. Where the original graph has zeros, the reciprocal graph has vertical asymptotes, you can't have division by 0. The next big idea is a reciprocal doesn't change the sign. So if this is a negative f value, then 1/f will also be negative. So I know the graph will be above or below the axis in the exact same way. This is below the axis, so this guy will be below the axis. Then it'll go above, then below, then above. So I know my graph is going to be in those regions. Now the only question is the shape. So if I then talk shape, the last idea is the reciprocal idea. In terms of the numbers you get, when you take the reciprocal of a big number, you get a small number. And so when these guys are big or far from the axis, this will be small or close to the axis. So this is big, the reciprocal is small. As this gets small, what's 1 over a small number? A big number. So as this gets small, negatively, this guy gets large. This guy, again, small positives here would have reciprocals that are big positives on both sides. And then it would come in and max out. Now don't worry about how low. Calculus actually solves that question. How low should you go? Just for now, have some kind of between two asymptotes parabola E shape there. Same goes here. Large negative, small negative. You could actually probably take a stab at this. This is about 4, right? What's the reciprocal then? 1/4. So I actually should be about 1/4. But again, don't worry about that. Look. All right. And then finally, positives should be positive. As this gets big, this guy gets small. As this gets small, the reciprocal gets large. 4 big concepts. Asymptotes above or below the axis in the same way, and then big reciprocals are small and vice versa. With me? Okay, 17. Questions on 17 still? Does whoever asked that need that still? Okay, good. Let me know what I can do to help you. If you've been getting stuck on anything individually, let me know. I'll be around. And that is good.